Alright, welcome back. If you haven't seen these videos before, just a little disclaimer that I'm not attempting to teach this class per se. I am just trying to study for this course. I am currently taking this course, actually. These videos just help me really solidify like my own thought processes on these definitions and theorems and like kind of help me put everything together mentally. This video is section 13 of chapter 2 of Munkres' Topology second edition, and we are going to be talking about a basis for a topology. So, jumping right in, a little bit of motivation for a basis is in section 12, especially with the example of like A, B, and C, something very small and finite. It's very easy for us to start to describing those topological spaces, but obviously, as is with most mathematical courses, we're not necessarily concerned with the finite instances. We tend to be more concerned with what happens whenever we have infinite sets, like R or Q or Z or any of those, right? What do we get when we start working with those? So it becomes very difficult for us to describe topologies on infinite sets like how we were doing in the previous one. So that's kind of our motivation for a basis. And with that, we'll kind of jump in on a definition. So if X is a set, a basis for a topology on X is a collection, and once again we're going to kind of use some of our fancy notation here, so that's going to be a cursive B of subsets of X. These are called basis elements such that, so we have some conditions that we need to meet here. So the first one being is that for each, in this we say X slash, hold on, I need to double check some of my notation here. It's definitely been a minute since I've used latex for things. So let me see. I think it literally is just the word in, if I had to take a shot in the dark at it. I apologize. Feel free to just kind of skip through this. Yeah, okay, yeah, it literally is just in, so I was right. No need for me to just go against my gut there. In X, get rid of this extra space in there. There is at least one basis element, just a regular capital B, containing X. And then the second one we have to meet is if X belongs to the intersection of two basis elements. And I'm going to kind of just flip over to Unicode for this one because it's going to be a little quicker to type. Then there is a basis element, which we will call B3, containing X such that, containing X such that, E underscore, I meant to type 3 there. And I'm pretty sure like I could just have my symbols in here that are just quick and easy. No. Okay, so slash subset of B underscore 1. Okay, I'm just making a fool of myself at this point. Okay. There it is. What is it? Oh, it's cap. What? Okay, whatever. b underscore 2. Sorry about that. Made a little bit of a fool of myself there. Okay, and then we say, and I'll jump into kind of like how I'm reading this here in a second. So we say if, then I'll switch back to latex here. So if B satisfies these two conditions, then we define the topology topology T generated by, and this is generated by this B over here. As follows. Oh my gosh, it's bolded, my bad. As follows, a subset U of X is said to be open in X. So little note here is that is to be an element of, and then that's this guy right here of T, right? I'm bolded again, my bad. If for each, and once again we're going to jump into X slash in. Oh dear. Oh gosh. Oh my. Oh no. Oh no. What did I do? What did I do? Oh my gosh. I'm so sorry. I have no idea what the heck I did. I don't know where that southern drawl came from either. Okay, let's get back into the always inserts an extra space for whatever reason. So in U, there is a basis element. Whoa, hey, that's funky. B. B belonging to my collection. Sorry, this definition is a little lengthy. I promise I'll talk on it here in a second to kind of like talk through my thought process. There is a basis element, and we're going to come back here. That's B slash N slash mathcal B. Such that I'm just going to kind of like a little Control C, Control V action over here. X is in B, and B is a subset, and B is a subset of U. Okay. So that kind of wraps up our first definition here. Sorry, it kind of took a while to get her out into the world, but I don't know why this is. Did I? I did. I don't think I spelled it wrong. I don't know why I was doing that. Okay, so if X is a set, a basis for a topology on X is another. So we have a collection B of subsets of X, and each of those sets are what we call basis elements. So this ties back to section 12, where the elements of a collection are sets. So the basis elements are sets themselves, such that for every single point inside of X, there's at least one basis element that contains that X. So all of my basis elements, so every set of basis elements needs to contain every point inside of my space, right? Now, if X belongs to the intersection of two basis elements, B1 and B2, then there will be a third basis element that also contains X. That is not the intersection of those two. Then we also jump into this idea of openness again. So if we harken back to our section 12 definition of openness, the definition of open was that a set is considered open if it is inside of my topological space. So your topological space was that collection, right? So a set is open if it belongs to the collection of sets that form your topological space. So if my collection B satisfies those two conditions, then we say the topology T generated by my collection B is a subset. So we say a subset U of X is said to be an open in X, because remember, that goes back to it's just inside of my collection that forms that topological space. If for every X belonging to that U, there is a basis element that contains there's a basis element that contains that X, and that B is a subset of U. So let's go ahead and just try to get a little bit of visual intuition as to what this is kind of talking about and referring to here. So let's just draw a simple picture, right? I'm not really going to be focused on drawing like a space X here. Let's just kind of draw a singular point. So let's just draw a singular point X. And let's say that I have one basis element that goes this way and one basis element that goes this way. So I'll call this B1 and I'll call this one B2. So I have an intersection of basis elements, and X is contained inside of those basis elements. So what this is telling me is that this is property 2 of the basis definition, is that there will be some sort of B3 that is not comprised as the intersections of these guys, right? So in other words, we're really starting to jump into the idea of like neighborhoods at this point. Once again, you should be familiar with neighborhoods from an analysis course, but this is kind of starting to creep into that idea. I wouldn't say this is like the definition of neighborhood by the way I'm interpreting it, but I think you can start kind of like seeing some gears turn as to what that might mean here. We could also draw rectangles. I think Munkres also uses the idea of rectangles. So I'll draw a rectangle here. Let's draw a point X here. And draw another rectangle over here. And I think he called this B prime 1 and B prime 2. And so there must be some, once again, by our definition, then there has to be some B prime 3 that would go around this X, because that's our intersection at that point, right? Now, the note that Munkres makes about these two shapes is the basis that's generated by these B primes will actually generate the same topology on the plane as the basis of B over here. So what he's really trying to get at here is that these rectangles and circles over here, they're going to kind of perform the same task. Another example that he throws out there is if X is any set, the collection of all one-point subsets of X is a basis for the discrete topology on X. So we're talking one-point subsets. That is, keep in mind, like that could be like a singleton like A. That can be something like AB. So we're just constructing stuff like this. Now, once again, it's automatically assumed that the empty set is already inside of here, just because that's the definition of construction here. But let's do a little check here, because we just kind of like threw out there that the topology T generated by my collection B is a topology. without like actually like fully checking it just quite yet. So let's just go ahead and do like a quick little visual check on that. So um, we're going to be kind of using this idea of U, of that open set, right? So remember our definition said that a subset U of X, and I'll just flip back. A subset U of X is said to be open in X. That means that it's an element of T. Keep in mind that we're talking about sets here, so a set is an element of a collection. If for each value, for every point that belongs to there, there's a basis element. A basis element, in this case, that's a set B, belongs to my collection of sets, cursive B, such that X belongs to the set B, and the set B is a subset, and get rid of that extra space there, of U, right? So if we take U to be the empty set, it's going to satisfy our condition of openness. It's pretty trivial. Um, kind of the same for if your entire set is also inside of that collection, since every single X belonging to your set, there's going to be some basis element B containing X that's also contained in your entire set X. I guess like a little bit more visually on that front. Keep in mind, I'm going to be trying to do my best for visualizations, but this is an inherently abstract concept, and so there's only so much that I feel like I can do without having to like delve into something else to really kind of pull up a visual for something. Um, so if sorry, going back, if X is inside that collection T, uh, we're basically saying for every X belonging to X, there will be some, so there exists some basis element B that contains X uh, and is also, and B is also contained in X. Basically, like if I have some, and keep in mind this is like a pretty broad generalization. Like if I have some space X that's defined like this, and I have some point X inside of here, all this is saying is that I can draw a circle around here and call that a basis element B. It doesn't have to be a circle, but that's kind of like the gist of what it's saying. Now let's go ahead and work on the union side of things. Let's go ahead and say, so this is going to kind of like check off our first condition, and also put this guy in there. So this really checks off our first condition. Our second condition involved the arbitrary unions, right? So let's go ahead and bust out that U alpha once more. You'll kind of notice that that's a very common term that Munkres likes to use, so I'll just kind of run with it as well. What we want to do is we want to prove that the arbitrary union of these is inside of my topological space, right? We say that, like, let's let U equal the indexed union where alpha belongs to some indexer j of U alpha in this instance. And we know that that belongs to my topological space here. Sorry, not belongs. We want to show this. Let me correct myself here. This is what we want to show. Like, this is ultimately what we want to show and prove. So let's say that we have some X that belongs to this union, right? Then there exists some index alpha such that X belongs to one of these guys, right? So if X belongs to this big old U over here, well, this U is comprised by a union of a bunch of sets, right? Well, then X has to belong to at least one of them. It can be in more than one, but it just has to be one, right? Now, what we know here is we know that U alpha is open. And that's because the way we're composing this is uh, this is an indexed family created from my topological space. So if I'm creating indexed sets from my topological space, well, the definition of an open set is that it was something inside of the topological space. So if I'm grabbing a set from the topological space, then that means it is open. So I know that U alpha, so I know U alpha is open. So since it's open, there exists a basis element. There exists a basis element B such that X must belong to B, which is a subset of that U alpha, right? So that means, so I'll just say, I'll say thus in this instance. So I'll say thus X belongs to B, and B is a subset of U in this instance, right? Because if it belongs to some U alpha, then it has to belong to U as a whole, because U is composed of those arbitrary unions of U alphas. So, um, uh, so U is open. In this instance. So this kind of checks out at this point. Um, our arbitrary unions fall back inside of it. So just remember that us showing that U is open means that those arbitrary unions are inside of that collection. Because the definition of open sets, once again, is that it is inside of my collection that forms the topological space. So basically, like if I kind of like walk through the logic of this proof again, because once again, like I kind of need to solidify things for myself here too. If X belongs to this big U, right? Like we just pick a point inside of there, then there has to exist some index that it belongs to inside of here. Well, we know that this index right here is created from this topological space. So that means it has to be open. So since it's open, there has to be some sort of basis element B such that X belongs to that basis element, because once again, if you have a topological space, then you can form basis elements of that topological space. So there has to be some basis element that contains X that is also a subset there, right? So that means X has to belong to that basis element, and that basis element is a subset of this big U over here, right? And so since that basis element is a subset of our arbitrary union, that means that that arbitrary union must be open by definition. All right. So we're going to jump down into step 3, and I apologize if I'm not giving the absolute best explanations. Once again, I'm not necessarily attempting to teach the course. I'm just kind of talking through my own thought process here, and what may make sense to me may not make sense to others, so I apologize. Let's go ahead and follow kind of what Munkres shows in this portion. Let's see. Sorry, double checking some notes here. Okay, so Munkres is going into finite intersections at this point. So let's assume that we have some finite intersections going on over here. So we have U1 intersected with blah, 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 all the way up to UN. We want to show that this belongs. We want to show that this belongs here. So this is our show condition. Now, if n equals 1, then duh, yeah, it belongs inside of here. That's fairly trivial. Now, let's go ahead and use a little bit of induction here. So let's say that U1 intersect dot 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 intersect UN. Well, this is really the same thing as us saying U1 intersect dot 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 intersect UN minus 1 intersect UN. So let's go ahead and just suppose that this is true. So I'm just going to go ahead and suppose that this portion is true, right? So we're just going to prove it for n. So by the hypothesis here, we know that this portion, so I know that this portion must belong to my topological space in this instance. And so the intersection of these guys is inherently going to belong to T. This seems like kind of a bit of a jump in the book. Let me see. Let me see if there's a better explanation of it that I can make sense of, because it seems like he just kind of made a jump. Okay, hold on. Okay, so let's kind of put this on the shelf for a second. I apologize once again. This isn't really meant to be teaching, just kind of meant to me kind of making sense of this. So let's just look at an element. Let's look at the case when n equals 2. So I have U1 intersect U2, and I want to show that this belongs to T, right? So let's say that X belongs. So let's say some point X belongs to this intersection of U1 and U2. So I'm going to choose a basis element. So I'm going to choose a B1 containing X. So this contains X such that B1 is a subset of this U1. Now I am also going to choose, so also choose, oops, so I'm also going to choose some B2, so another basis element B2 that also contains X, such that B2 is a subset of U2, the band, obviously. Bad joke there, sorry. Now, the second condition for a basis element allows us to choose some B3, right? So let me kind of like visually draw out what's going on here. So I have some point X. So I have two big ol' subsets going on here, right? So I'll call this U1 and U2 going on over here, right? So inside of U1, I have this basis element, B1. And then inside of here, I've got this basis element, B2, that are containing it, right? Now, by my definition that I constructed over here, if X belongs to the intersection of two basis elements, then there is a basis element B3 that contains X, right? So what I'm saying is that there is some B3. There is some B3 going on right here, right? So by that definition, so we say then X belongs to some B3, and B3 must belong to the intersection of U1 and U2. So that means So U1 intersect U2 must belong to my topological space T. And once again, that's by definition right here, right? So if I'm able to form a basis element inside of here, well, those basis elements are going to form that topological space. And if something is inside of that topological space, then it is open. So this U1, U2 is open. And so this proof up here is really just kind of like cruxing off the proof that, well, if I were to go to U1, U2, and then U3, well, then I just group U1 and U2. Well, I know that that's inside the set, and then by the same logic that if I intersect another one in there, well, then that's also going to stay inside of it. So we check it off. This does form a topological space whenever we're dealing with basis elements. So jumping over to another definition, except this is now a lemma. This is actually lemma specifically 13.1 in the book, just in case I need to go back and reference it. So let X be a set, and let, I'm going to steal this B, this B for boy over here. So I'm going to let B be a basis for a topology, and then that's going to be my topology T. On X, then T equals the collection of all unions of elements of B, of my collection B, more specifically. Okay, so what is this lemma really trying to get at here? So Munkres is specifically saying this lemma states that every open set U in X can be expressed as a union of basis elements. So this lemma seems like it's pretty powerful to me, honestly, because every single open set can be comprised of a union of basis elements. I feel as if that's like very, very important here, so maybe I'll make a note of that. Any open set U can be expressed as the union of basis elements B. So once again, that feels incredibly powerful to me, and I feel like that's something we're probably going to wind up using quite frequently in this course. So something Munkres points out is we're going from a basis to the topology that the basis generates, but sometimes we need to kind of go in the reverse direction. So this kind of ties into, and the proof of lemma 13.1, I'm not going to delve into that personally here. You could feel free to look it up, but that's going to make the video a little bit too long, in my opinion, if I were to touch on that. Still got quite a bit of section 13 to kind of chug through here, and it's getting pretty late at night, if you can't tell. So lemma 13.8, so let X be a topological space. So now we say suppose, and we are introducing a new letter. So suppose that C is a collection of open sets of X such that for each open set U of X and each X in U, there is an element of C, the old copy-paste gang. There's an element of C such that X is in C, which is a subset of U. Let me say then C is a basis element, is a basis for the topology of X. Okay, so let me read into this here. So let X be a topological space. So we're already guaranteeing topological space on this set. Suppose that a collection C of open sets of X, such that for each open set U of X and each X in U, there's an element of C, such that X belongs to C, which is a subset of U. And C is a basis for the topology X. So the way I'm reading this is it really just ties into the definition that we're going into, which is why it's a lemma, because it really just ties into the definition. So suppose that we have a collection C that's comprised of open sets from X, right? So if I were to go back to that ABC example, if I were to take the discrete topology on that ABC, let's just say that my collection, because there's nothing saying that that collection has to be a topology, right? So like, what if I just made that collection the singletons? So what if I just had A, B, and C as singleton sets inside of my collection C? Such that for each open set U of X and each X in U, okay, so for each open set U of X and each X in U, there's an element of C. So there is a set inside of C such that X will belong to that subcollection, which is a subset of U. Okay, so my singleton set, throw that idea out the window, because the way this is being constructed here is this seems like very strong in how it's making its definition, which like I guess that's the point. Like early on in a text, you need to make something like pretty strong to begin with. But the way I'm seeing this is for each open set, so for every set that belongs inside of my topological space, and each point that's inside of those sets, there will exist an element, so a set of C. Okay, then C is a basis for the topology on X. Okay, so this really seems like it's a rewording of the definition to me. Like the more I think about this, the more it's like really starting to sink in and like make sense, because we have our open sets U of X, and we have all of our points inside of those open sets. Then there will be some sort of set inside of this collection. So I guess if there's a set inside of that collection such that X belongs to that collection C, which winds up being a subset of that open set U. So my collection needs to be a subset of that open set. So let's say my open set was AB, then I could have, yeah, so like let's say, let's go back to kind of like that basic example of like let's say X, like that's my set and the topology generated on that set, like let's just say what do I need here? I need A and B, I think. The intersection. Actually, no, do it. No, I don't think so. No, I don't. I just kind of threw those in there willy-nilly. They don't actually need to be in there. Just another quick little verification. I have the empty set in my entire space. X union AB just gives me X. Union these two just gives me AB. Now we go to the intersections. X intersect AB is just going to be AB, so this does form a topological space. Cool beans. So the way I'm reading this is we have some sort of collection here, right? So like let's say that this is my U that I want to focus on. So this is an open set inside of here, right? And it contains 2 points, A and B. So what I'm saying here and how I'm reading this, yeah, this is kind of how I'm reading this, that my collection here, um, those points, so those points that are inside of U, so these are my 2 points that are inside of my open set U. There's an element, so there is a set of that collection. So these are my sets of the collection. So these are my sets of the collection, such that those points belong to that, right? So A belongs to here, B belongs to here, and that collection is a subset of my open set. And so that is, so A is a subset of AB, and B is a subset of AB as well. So to me, this is like a pretty simple example as to how to interpret that lemma. I think it is still derived from this definition up here. Once again, that's just kind of like the idea of a lemma in general, so nothing like too shocking there. Now we also need to tie this to the idea of finer, finer and coarser. So this is lemma 13.3. So we will let, I don't think I have that old B highlighted still. Let me just let B and B prime and B prime be bases for the topologies. And do I have a T? Can I get a T? T and, oh my gosh. T and T prime respectively on X. Then the following are equivalent. And then, so the first one is that T prime is, oh my gosh, I hate that it auto bolds, is finer than T, is finer than T, and for each X and X, I hate that freaking extra space, dude. Each basis element, oh my gosh, and each basis element be in, sorry, MathCal B containing X. There is a basis element B prime that is in B such that X belongs to B prime, which is a subset of B. Okay, so let's take a look here at what this limit is saying. So let B and B prime be bases for the topology T and T prime respectively on X. Then I gotta say then the following are equivalent. Get out of here. T prime is finer than T, so so basically, like, these will imply one another. So when we say the following are equivalent, is this one will imply this, and this will imply this. So if you can think of this as like an if and only if kind of reading situation. So if T prime is finer than T, then for every x belonging to my topological space, x, I guess my set x, and each basis element, B belonging to my collection B containing x, there is a basis element B prime such that x also belongs to that B prime. So I think this kind of like jives in my mind as to what the definition of finer is. So if you have a finer topological space, then that means it just contains more built out into it. So like if I jump back to my original notes from the first section 12, like if I go back and I look at like these two T2 and T3s, like T3 is finer than T2, right? Because there's just more of it in there. So if I think back in the perspective of this definition, well, if like a T3 is finer than T2 in that particular thing I just showed, then for every single x belonging to that x and each basis element B belonging to that collection of B containing x, there's a basis element B prime that also is inside of that collection of basis. That is also in that collection B, such that x also belongs to B prime, but is a subset of that first one, right? So, and each basis element containing x, there is a basis element B prime such that x belongs to that B prime, which is a subset of B. So let me think about it in this sense for a second. So if I have my T3 in this instance, which is finer than T2, we have AB, which does not exist over here. We have our basis element. Let me go back to the definition. And each basis element containing x, there is a basis element B prime. That's also in this x, such that okay. I'm getting that way to drive in my head a little bit more. So Munkres does give a pretty good, in my opinion, analogy here. So if we think about kind of like our smash and rock example, right? We can think of our rocks as like the basis elements of the topology. And once we smash those rocks up into really tiny pieces, the dust particles are now the basis of a new topology. And so the new topology is finer than the old one, and each dust particle was contained inside of a pebble, right? So what this is really saying is if I were to take my topological space and make it a lot finer, well, I've just smashed up those original pebbles a little bit more, right? So those now form new basis elements of that set, right? We have a new definition to tackle on now, and that is of the standard topology. So we say if B is the collection of all open intervals in the real line, the topology generated by B is the standard. Is the standard topology. So just to kind of like write out that a little bit better for us here. So what we're saying is we have all open intervals in the real line. So that's of this form AB. So this is defined as the set X such that A is less than X, which is less than B. Right here, right? So it's the set of all open intervals on the real line. So the important note here is that whenever we consider R, right? So whenever we consider the reals, it is equipped with the standard topology. So that is the default topology we are associating with R in this instance. If R is being equipped with any other topology, we will specifically say that it's being equipped with other topologies. If you just see R kind of, hanging out there in the world by itself, then it's going to be just the standard topology is what you would assume on it. Now, if we were to take the half-open intervals now, so I'm going to call half-open intervals like this, and that's defined as the set X such that A is less than or equal to X, which is less than B. This is what we call the lower limit topology on R. So this is the lower limit topology on R, which I believe we will see denoted as R sub L. So whenever you see R sub L, that's going to denote the lower limit topology. One more topology we are going to touch on here is the what's known as the K topology. So what we are going to do is we are going to take all open intervals and we are going to essentially subtract this K from it. So we're going to take all open intervals A, B, and we're going to take away this K. Now, what is K in this particular instance? Well, K is defined as the set of 1 over n, such that n is a natural number. Now, you may see positive integers written in here. When I am personally writing the naturals, I do not include 0 in that, just to avoid ambiguity whenever we're saying that. But this is known as the K topology. And you will see this denoted for R with a little subscript of K. Now, all of these collections that we just talked about, the standard topology, lower limit topology, and K topology. Now, also, side note, there is also an upper limit topology. If we were just to flip this for this to be open and this to be closed over here on this B, that does create the upper limit topology. Just a heads up, that does exist as well. All of these are bases, right? We can start defining the relationships between these topologies, which is going to lead us to another lemma here. This is lemma 13.4 in the book. The topologies of the lower limit topology on R and the K topology on R are strictly finer than the standard topology on R, but are not comparable with one another. So let me kind of write that down here for us to look at. So what we are saying is that RL is strictly finer than the standard topology R. So remember, that's the direction of finer. And we are also saying the same for the K topology on R. But what we're saying is RL and RK, they are not comparable with one another. So, sorry, just getting a little notation out of the way. So these two are not comparable with one another, but we do have strictly finer over here. So let's go ahead and just kind of like walk through a pretty simple proof on the finer aspect of it. Munkres does leave it as an exercise to show this portion right here, which I do believe is actually one of the exercises given in this exercise set. Yeah, exercise 13.6. Show that the topologies of RL and RK are not comparable. So that is something I can probably just work in the exercise section of it. So the first thing is we are going to, and I'll go ahead and just write proof here. So we are going to focus on T prime, and T double prime in these instances. So I'm going to go ahead and let T be for the standard topology, T prime be for the lower limit topology, and T double prime be for the K topology. I'm not like full-blown writing out this proof because I am writing with a mouse, if you can't tell, and that makes things significantly more difficult for me here. So what we do know is that a basis element for T1 is of form A comma B, right? And a point X, so let's say we have some point X inside of that interval, right? The basis element of this guy right here, where we can just say like X comma B, right? Like we get to build this thing however the heck we want. It contains X, so like let's say X belongs. I guess I could write this out like a little bit better. So let's say that X belongs inside of this interval, right? Well, I can just construct an interval in the lower limit topology where my lower bound is X and then my upper bound is this B value, right? And there's nothing that's stopping me from doing that. Well, that means it lies inside of AB. Now, on the other hand, like I'm just going to kind of show that it's not the other way around, where the standard topology on R is not finer than this guy over here, because that is something you have to worry about. And actually, I wouldn't say worry about, something you have to think about. If we are given if we're given a basis element to start with, in this case X comma D, well, then there's no open interval AB that's going to contain X and lies completely within this range, because I'm basically defining D to be larger than B in this instance. So it goes one way but not the other way. So what we would say is that it's strictly finer in this particular instance. So the lower limit topology is strictly finer than the standard topology. And now a very similar argument goes into the RK side of things. So if I make the same argument that I have some X belonging to AB, so we construct like a very similar argument where like we have X belonging to AB. The way we have this constructed inside of here is that, well, X can belong to this guy over here. So we'll say that this is strictly finer. A counter example for the other way around is if I specifically pick this basis element right here, -1 to 1, less this K value. So the point 0 of this interval, there is no open interval that contains 0 and lies inside of B in this particular instance. Because keep in mind, like these ends, like this is going to keep getting closer and closer. So it's really, really difficult to like find a neighborhood that's making this open. And once again, the proof of these not being comparable is an exercise that I could potentially work in the next video. We'll see which ones I decide to work. The last definition that we need to touch on before before I end the video, is the idea of a subbasis. So a subbasis, and this is how it's spelt in the book. He spells it double B, not single B. So I'm just rolling with how he spells it. So a subbasis. Now we're introducing this new letter S now, right? A subbasis S for a topology. Oh my gosh, the frickin' bold and italicized. For a topology, X is a collection of subsets of X whose union equals X. The topology denoted by the subbasis, and once again I shall pull the old copy trick, is defined to be the collection, in this case T, T of all unions of finite intersections of elements of S. Okay, so let's think through this definition. So a subbasis S, so it's a collection, for a topology on X is a collection of subsets of X whose union equals X. The topology generated by the subset. Okay, so let me think back to like a basis topology versus a sub-basis topology. So it seems like so it seems like the big difference here is that a sub-basis is where the union of the collection on X is a collection of subsets of X whose union equals X. So the topology generated by the subbasis is going to give me all of X, and the basis topology, not the subbasis topology, that union does not have to equal all of X. And that seems to be the primary difference between the two. Any less thoughts for me on that? The topology generated by the subbasis S is defined to be the collection T of all unions of finite intersections. The topology is defined to be the collection T of all unions of finite intersections of elements S. Okay, so that's... oh man. He really just kind of like threw that in there without giving a whole lot of explanation to it, huh? Really decided to put a lot of the thought into you letting you trying to discover what that is. Okay, so topology generated by the subbasis S is defined to be the collection T of all unions of finite so all possible finite intersections. If you union them all unions of finite intersections. So if I were to have like U1 and U2 intersect, and then like U3 and U4 intersect, the union of those two intersections now forms a set. And if I were to keep doing that for all of them, like all possible combinations, that now forms the subbasis topology, is how I am interpreting that. So a little bit more, I guess, like visually speaking, is if I were to take like U1 intersect U2, and then union that with like U3 intersect U4, and this is like a complete example here. This forms, oh my gosh, that was very ugly. I'm so sorry. A little bit better. So that now forms an element. So that's one element of T. And if I were to keep doing that for all possible combinations of these and keep unioning like all possible union combinations of these, that would form all of my elements, and that would form that topology, is how I'm understanding it. But with that, that's going to wrap up this video over the basis for topology. I will be working exercises in this next video to kind of demonstrate, not necessarily demonstrate, but just kind of like tie some of these concepts and ideas together. I'm not going to work all of the problems. I'm just going to kind of pick a select few, and then the video after that will be over the order topology. All right, have a good day. Thank you.